All right, section 6.3, we're taking a look at something called separation of variables. So there are some types of equations where we're able to separate the x's and y's. Okay, these equations are called separable. So we can separate all the x parts on one side, all the y parts on the other side, and we're able to do some sort of integration, typically speaking, and then finish the problem. Not all problems have the ability to separate variables. It doesn't always work. So a real quick example you can maybe think about is, let's say you had a trig function where it had an x plus y as the angle, or even x times y, right? Like that's not an easy thing to separate. You might be able to use some fancy trig identities, maybe, but you might not, right? There might not be a way to separate those at all. But the ones we're going to be taking a look at in section 6.3, they will always be able to be separated. So it's kind of a helpful hint, right? You're going to be able to use the methods that they're describing for everything in this section. So let's take a look at an example. And some of these things you're going to feel like, isn't this kind of like what we've done already? And the answer is yes, we're building upon it. So these are similar things. So we're going to find a general solution. So general solution means we're going to have that plus c at the end of the equation, square root of x squared minus 16 y prime, excuse me, equals 11x. So what we're going to do is we're going to move all the x's to one side, all the y's to the other side, and we may need to shift a little things around as well as we do so. So let's start with shifting this x squared. So we're going to divide the other side, well, both sides, by x squared minus 16's square root. So square root of x squared minus 16. So this leaves us with y prime on the left, but it's better for us eventually anyway to write that as dy dx. So let me do that at this point too. Y prime is the same as dy dx. And then on the left, I have 11x over the square root of x squared minus 16. Now, we've almost separated the x's and y's. What's still not separated? The dx. And that's simple to do as well. We're just going to shift it by multiplying it to the other side. So this is dy equals, and I've got the 11x over the square root of x squared minus 16, and then dx. Okay, so far so good? What are you going to do next? You're going to integrate, right? So we're going to do an antiderivative on both sides. What is the antiderivative of dy? That's just y. Now, technically, it is y plus c, right? But we're going to have a plus c on both sides, not necessarily the same value, and we would be able to merge them together. So we're just going to write the plus c on one side or the other, and typically speaking, we'll write it on the right-hand side because there's usually more going on in terms of x than there is in terms of y. On the right-hand side, how am I going to take an antiderivative of 11x over the square root of x squared minus 16? Yeah, we don't have a lot of tools, right? Remind you again, right? We haven't done chapter 8. I mean, we have, but the book hasn't. So there's not a lot of options. This would be a u substitution. What would u be? Yeah, the part that's underneath the radical, x squared minus 16. So then the du would be 2x and dx. Now, I don't have a 2 in my problem. I have an 11, but that's okay, right? That's okay. So we're going to divide both sides by a 2. So over here in my original problem, I'll pull my 11 out in front and my over 2 out in front. And then this will have a square root of u in the denominator and du in the numerator, or we can write the d over here and a 1 up here, which is how we usually do. Now, there's nothing wrong with it the way that that's written, except that, we don't really do it that way. I'm going to move this over to the side so I have some more space. So it's much more common for us in terms of finding an antiderivative at this point to have that written as y equals 11 halves. That part's fine. And then the integral of u to what power? Yeah, negative 1/2. You got it. All right, so now we're going to be able to integrate that. So we have y on the left. We have 11 halves to start with on the right. What's the antiderivative of u to the negative 1/2? Over 1/2, sure. U to the 1/2 over 1/2. And then I do need a plus c, so we will put that plus c right there. There's an over 2 and an over 1/2, so whatever point you decide to simplify, these do cancel because you're dividing by 2 and dividing by 1/2. Similarly, if you don't like me canceling it like that, you're welcome to see it be rewritten as 11 halves instead of dividing by 1/2, you're multiplying by 2. like this. So either way, you're sort of picturing it, the 11 or the 1/2, the 2 in the denominator and the 2 that are outside of it, or the 1/2 in the denominator, are going to cancel. And then it is a little bit more friendly for us to rewrite this as square root of u, and we need to because that's how the problem started. What's my last thing to do then? Yeah, put the x's back in, right? This is x squared minus 16. So this would be my general solution for that differential equation. Okay, what do you think? Doesn't feel that much different than the things we've been doing, right? It shouldn't. It's very similar. All right, this one asks us to find a particular solution. Particular solution always means that we've got an additional piece of information given at the end that we're able to use to evaluate and figure out what C is, right? That's the idea. But the beginning part looks just like what we did in the last problem. We need to get all the x's on one side, all the y's on the other side, shift some things around. So the first thing you might notice is that there's addition and subtraction, right? There's a subtraction there. So separating it by moving that to the other side is a very friendly kind of first step to write this so that there's a piece on each side, right? We're not dividing or multiplying, we're just rewriting that piece. We can divide by our 2x. So, and then instead of rewriting it as y prime, let me go ahead and write it as dy dx at this point. You could have written it that way, but earlier, that'd been fine too. And I know I'm doing several steps at once, but we can move the 2 down, right? That's a property of logs that'll be helpful for us. So if I move the 2 down and I have 2 natural log of x over 2x, what will also happen? Yeah, the 2's are going to cancel. And the goal to have dy on the side by itself means I need to move my dx, right? That's going to always be one of our steps. So dy is going to equal now natural log of x, over x, and then dx. This is a good place for us to be, right? It's a good place for us to be. We integrate. How do we integrate the right? It's another u substitution. So the left is just y, right? dy derivative, it's y. Sorry, antiderivative is y. If I do a u substitution, what is my u? It's natural log of x. So remember, anytime we've got a natural log showing up, it's going to have to be the u because you do not have a closed form aside from a table. Or integration by parts. We saw that on our last test. But to do that, and we haven't done either tables nor integration by parts if we haven't done Chapter 8. And we haven't at this point with Chapter 6 material. So this will be the u, because what's the du then? 1 over x. That's the other piece that we have, right? And there's my dx. So this will be rewritten then as the integral of u to u. Does that make sense? Excellent. You know how to find an antiderivative of that. What is the antiderivative of u? U squared over 2, or feel free to write it as 1/2 u squared. And I need plus c. Thank you. Yeah, I need a plus c. So I'm not quite done. I've got it still in terms of u. I need to put it back in terms of x's. So this is y equals. I'm going to write my over 2 as 1/2. And then I have the natural log of x squared. This 2 does not pull down in front. Why? Yeah, it's not on the x that's inside of the log, right? It's on the entire expression natural log x. So be careful, because you might look at that and move too quickly and think you can. It looks like it'd be really nice to, right? But it doesn't have that feature. So then we have our plus c. If I were doing the last problem, I would be finished at this point. This is a general solution for this differential equation, but I wasn't asked to find a general solution. I was asked to find a particular one. So the last thing that I do when I'm asked to find a particular solution is use the other piece of information. It tells me y of 1 is equal to 2. So that means the y value is 2 and the x value is 1. Our c is 2 because the natural log of 1 is 0. So this whole thing right here is 0, which makes all of that 0. So c is 2. And then our final answer, that is our particular solution, is y equals 1/2 natural log of x squared, and then plus 2. It probably is worth noting here that you could, depending on what initial value they give you, have a c value that doesn't just look like a number, right? Like it could actually have looked at the end like, 1/2 natural log of 3 squared. And that could be the c. So as you're taking a look at what you get for c at the end, don't necessarily expect it to just be like 5. Right? It could be a value with no variable in it, right? It doesn't have any variables, but it doesn't actually look like numbers that we work with sort of since, first grade kind of stuff. So keep that in mind. All right, let's take a look at the next one. All right, what is this question asking us to do? We haven't done this for a while. What are we finding? An equation, right? An actual equation of a line. So it says find an equation of the graph, in this case, that passes through the point and has the given slope. So that's a little bit of a different question. So we're going to start out with the information that the point that's being given is 9, 1. And our differential equation is y prime is equal to y over 2x. Okay, same process to start with, getting y's on one side, x's on the other. This one doesn't have as much, on the outset looking like it doesn't have as much going on, but the separation of it looks a little bit different. So we have dy dx is y over 2x. So both sides of the equation have x's and both sides of the equation have y's. So what am I going to do to separate these? Okay, say it again, Andrew.
Multiply the dx and the 1 over y.
Okay, so we would multiply by 1 over y. That's going to move the y. I agree. And you want to multiply, I'm going to give me some space here afterwards. Multiply it by dx to move the dx. So this piece cancels here, and this piece cancels here. And if you want to do it in 2 steps, by all means, do it in 2 steps. Is that okay? So what it ends up giving us then is we don't just have dy on the left. We have 1 over y dy. That's different. We haven't done that today. And then I have 1 over 2x dx. Now I've done something kind of like 1 over 2x. It wasn't that same expression, but where I had some stuff in the denominator. So what's my next step then? Yep, finding an antiderivative, right? All right, so what is the antiderivative of 1 over y? There you go, natural log of, somebody said it, absolute value of y. How about the antiderivative of 1 over 2x? It's the natural log of something. It's not the natural log of 2x. It's a 1/2 in front, and then the natural log of x. So when we're seeing this, we need to be thinking about the fact that we have a 1/2 here, and then we have a 1 over x here. There is a constant multiplier going on. Yeah, some nuances I wanted to bring your attention to, reminders. You've seen it before, but it's been a minute, right? I'm missing one thing. What am I missing? Plus c. Okay, pretty good so far. All right. The goal is to solve this for y, though. And right now, the y is inside of a natural log. This goes all the way back to the beginning of the semester, chapter 5 stuff we did. Do you remember how we get that y out of there? E. Yeah, the inverse operation, right? Like the way that you undivide something is you multiply, like multiplication and division are inverses. Well, logs and powers are inverses. That's what it is. And the log that we're using here is a natural log, which means it has a base of e. So the inverse of the natural log is e as a base. So we're going to put e as a base on both sides. Now it looks a little bit funny, but if you think about sort of rewriting it, maybe it would have looked a little bit better. So if I had shifted this, if I put my equals down sort of in the middle, now it looks a little bit cleaner. But this is the perspective. Yep.
Does the e cancel out like the absolute value?
Yeah, because e does not have any care, so to speak, about whether or not you have a positive or negative inside of the log. So when we cancel the e and the natural log out, the absolute values will also eliminate. So we'll just have a y on the left. There is something to note here, though, and I believe that it came up in section 6.2. When we take e to a power like this, right, the entire power included the c at the end, correct? So I don't have a plus c on the baseline anymore. The plus c is in the exponent of the log part, right? Not the log, in the exponent of the e part, right? Okay. So when I'm looking at this, there's several things. This 1/2 can come up here, right, as an exponent on x. So when this cancels, the e, I'm going to rewrite it a couple times probably here at least. So this is x to the 1/2. And then I'm going to rewrite this as e to the c. That's property of exponents as well. If you have addition of exponents, it's the same thing as having the exponent to the powers. Let me write it out in the form that you're used to seeing. A to the m plus n is a to the m, a to the n. Does that look familiar? Some algebra 1 kind of things. So that's what we're using. We usually think about it going this direction more than the direction I've written it, but it's an equality, which means it can go either way. So this is able to be separated out down here. Out of space. Let me move this. All right, and so what happens to the e to the natural log of x to the 1/2? Just to x to the 1/2. So I now have y equals, and I have x to the 1/2. We'll rewrite that in a second. What about the e to the c? What is that? It's some constant c, right? Now, it's not really the same constant c. So if we want to be a little bit more clear, we can go back up and we can call these each c1s, right? It's a different constant. I'm not getting the same constant. But e to the c is a constant. So I can write it as a multiplication factor of c instead of an addition and an exponent kind of factor of c. And if I rewrite this just a little bit, this looks like c square root of x. Now we're still not done, because what did it ask us for? An equation of a graph. Well, this is just another way of writing this. It's a particular solution. Because they gave me the ordered pair, in this case 9, 1, that's going to be a location, one of the points on this graph. So what do I do to find C? Yeah, I plug it in. You got it. So let me shift it up one more time so that I have more space. All right, so we're going to put in, which is where? We'll just let you tell me. The y is the 1, right? It's the second one. And the c is, the x is the 9, so it's square root of 9. So it's 3. So what is c? C is 1/3. So what's the equation of this graph that I'm looking for? Y equals 1/3 square root of x. All right. Any questions? Okay.